As I was saying, an example of negative feedback is the blood pressure regulation. So in this case, a change in the blood pressure is sensed in the baroreceptors in the aortic arch or in the carotid sinus, which are nothing else than stretch receptors in the walls of the aortic arch and of the carotid sinus. So, if the blood pressure increases, the stretch of the walls of these arterial vessels will stretch. And if it stretches above a certain, well, it's not really stretching above a certain level. This is a very finely tuned system, right? The more it stretches, the quicker the faster the afferent neurons fire, and the frequency of firing of the input into the medulla's vasomotor center will generate an orthosympathetic or parasympathetic neural response, where the parasympathetic neural response will lead to vasoconstriction, to increase blood pressure, to a response in response to a decrease in blood pressure, while the reduced sympathetic orthosympathetic response and potentially in certain cases increased parasympathetic, but parasympathetic response is not really, directly involved into the regulation of peripheral resistance, but mostly in heart function, which also, is involved in regulating blood pressure. But in any case, in more general terms, an increased orthosympathetic response will act on heart and muscular vessels to increase blood pressure in response to a decrease in blood pressure, while parasympathetic activity will act on the heart to lead to a decrease in blood pressure in response to an increase in blood pressure, which is the change in the heart rate and in the constriction of the vases. Um, Pretty much the same kind of concept in thermal regulation, right? So we do have our comparator, a group of neurons in the anterior hypothalamus, which will receive information about the body core temperature from the same hypothalamic neurons that are present in the brain, and which give you a direct information about the body core temperature and of the peripheral temperature. And any change in the body core temperature in respect to the set point of 37 degrees will lead to the activation of those effectors which lead to the production of heat. So, for example, the involuntary contraction of striatal muscles leading to shaking. So when you shake because you're cold, is because shaking produces heat. And also the activation of the brown adipose tissue between the scapular bones, which leads to the generation of heat by breaking down fatty acids. But on the other hand, if we do have an increase in temperature, we will have those autonomic responses, which will lead to more dispersion of heat, dissipation of heat, such as sweating. Another example of negative feedback is the blood sugar glucose homeostasis. So here you can see that if a person drinks at time zero a glucose solution, literally some water with glucose dissolved into it, what is going to happen to the plasma glucose is an increase, a peak, which then will be followed within few minutes by a decrease until, going back to physiological values. Plus, give or take around 30 minutes. And this is due to a very finely regulated mechanism by the endocrine islets in the pancreas. So we will talk about the pancreas a lot, but for now, just for you to know that the pancreas contains, it's a gland, right? And it contains both an exocrine function and an endocrine function. The endocrine function is carried out by these islets, pancreatic islets, which contain the sensors for glucose. And a glucose increase will be in the blood, will be detected by the pancreatic receptors in the islets. And pancreas will respond by secreting insulin, which is, a peptidic hormone which enters the bloodstream. Insulin will act on many targets, including liver and muscles, but mostly liver. And it will trigger in the liver the conversion of glucose into the polymer glycogen, which is nothing else but a polymer of glucose, de facto removing glucose from the blood circulation, so reducing the levels of circulating glucose. If, on the other hand, we do have a glucose decrease because we've been starving for a long time, pancreatic receptors will detect glucose decrease, which then will lead to the release of an antagonistic peptidic hormone, antagonistic towards insulin, of course. Not for the same receptor, but functionally antagonistic. Because glucagon still acts on liver, but it does the opposite thing that insulin does. It promotes the hydrolysis of glycogen in glucose. So what happens is that the insulin secretion on the administration of a glucose solution orally is that, will increase. And as you can see, there is an interval of plasma glucose concentration within which insulin secretion increases. So as long as the levels of insulin remain below physiological value of 100 milligrams per 100 milliliters, virtually there will be no insulin being secreted. But for values above that, the levels of insulin will, initially linearly increase and then more slowly at around 300 milligrams per 100 milliliter of glucose until it starts. And conceptually, the same occurs for glucagon. If the levels of glucose are below 100 milligrams per 100 milliliters, they will be, quite higher, certain times higher than normal, around 4 times higher than normal. And then they will go back to the value of 1 as soon as the concentration of glucose reaches 100 milligrams per 100 milliliter. So I'm pretty sure you can imagine a disease in which these mechanisms altered, and that would be diabetes. In a normal person receiving oral glucose, where the purple trace is glucose and the blue trace is insulin, you will see that the increase in plasma glucose corresponds to an increase in a peak in insulin, and the peak of insulin will correspond to a progressive decrease in the levels of plasma glucose until it reaches physiological levels. While in a type 1 diabetic person, which is a person which has impaired production of insulin from the pancreatic endocrine islets, also due to autoimmune kind of factors, even though type 1 diabetes is still a multifactorial disorder, there is a autoimmune component to it. In any case, the comparator is there, the sensor is there, but the effector is not there anymore. The islets are not able to produce insulin. And so if you drink glucose, you will see that the production of insulin is significantly impaired, and the levels of glucose will remain higher for several hours and at very high levels, over 250 milligrams per 100 milliliters of plasma blood, with all the consequences that we know. Hyperglycemia, we know, is toxic because it generates advanced glycation products. It can lead to blindness and all those things that you will study later on. Another kind of diabetes is the type 2 diabetes. But in type 2 diabetes is the receptors for insulin that are lacking. And that is often associated with obesity, which is a morbid condition and can lead to type 2 diabetes. And it's associated with increased heart and cardiovascular diseases and cancer. So type 2 diabetes is associated with obesity, and it corresponds to a decreased sensitivity to insulin. So once again, is the effector system being impaired, but it's not the production of insulin, it's the sensitivity, is the receptor for insulin, which is underexpressed on liver cells. More rarely, we do have positive feedback systems, which still have a very important role in human physiology. But I wouldn't say, I have to mention them here, but I wouldn't say positive feedbacks are directly related with the regulation of homeostasis in strict terms, as the maintainment of the internal environment, but they're definitely needed for the larger concept of homeostasis, which is the survival of the individual and of the species. Without oxytocin positive feedback, we wouldn't have childbirth. Without the formation of blood clots, we could die of hemorrhages. So definitely positive feedback systems where the effector system reinforces or amplifies the initial stimulus, is not homeostatic in the strict sense of the term, but is definitely homeostatic in the wider sense of the term, because it allows the survival of the individual and of the species. You can see why the vast majority of physiological systems use negative feedback, because it's harder to control a positive feedback. The responses are stable, and it becomes more unstable at each cycle. And this can be dangerous for the individual and sometimes even lethal. So these are some questions which I'm not going to go through with you. You give it a go just to have an idea of how good your learning is. Just to interrogate yourself if you understood the basic concepts we have been talking about today. And this is all for the homeostasis. See you soon to talk about body fluids. Bye bye.